Welcome back. Let's talk about goodness of fit, which is the type of hypothesis test we're developing in this section. A goodness of fit test is a procedure used to determine whether a frequency distribution is the same as some specified distribution. And again, that's a frequency distribution. Okay, the type of distribution we're dealing with, frequency or probability distribution. So, for example, regarding the economist studying the distribution of household income that we looked at above, what's the specified distribution and what distribution will she be testing? Well, the specified distribution is the one from 2000. So why is that? Well, she wants to know if the current distribution and that's of household income, of course, is the same or different than it was in 2000. Okay, so 2000 is the specified one. That's one that's known, and she wants to know, if the current one is different than that or not. So the known one that she's testing against is the one from 2000. The current one is the one she's testing. So what would the hypotheses be? Well, remember the null hypothesis is always about equality, sameness. So the null hypothesis is going to be that and I'm going to use the terminology that the book does so that when you read the book, it won't disagree too violently with the notes. So anyway, the null hypothesis is going to be that the random variable is the same as the specified distribution. Now, I'm using this equal sign very loosely. I'm using it as a shorthand for just saying they're the same. And by the random variable, he's talking about the distribution that we're testing. And what we're going to be typically, the word that's going to be associated this and what we do is observed values. So the distribution we're testing is something we've observed. So how about I make the note using observed values. So we've observed some data, and we want to know if the distribution of that data that we've observed matches or doesn't match some specified distribution. So then H1, the alternate hypothesis, is going to be that the random variable is not the same as the specified distribution. Okay, and again, by random variable, I mean the distribution of the data that we've observed. Now, something I need to mention, and I think that's why I'm focusing on this equal sign. Again, this not equal sign, it's not really a numerical not equal sign. It's my perhaps not good shorthand for saying that the two distributions are not the same, that they don't match. anyway, the reason I'm going on and on about the equals versus not equals is when we were doing hypothesis tests before for numerical parameters, the not equals version of the alternate hypothesis was always a two-tailed test. But this isn't really not equals. This is a different type of hypothesis test because we're testing an entire distribution against an entire distribution, and it's not really numerical. It's how well do they fit each other, okay? So the note that we need to make here is that even though I wrote not equals here, when we're doing goodness of fit tests, it's always going to be a right-tailed test. Okay, that's just the nature of it. So, what test statistic will we use for this right-tailed test? Well, let's let O sub I represent the observed counts of category I. Let's let E sub I, as before, represent the expected counts of category I. And I'll just remind you that we have a formula for E sub I. It's, what was it, probability of the ith category times the number of trials. Okay, so anyway, we have observed counts, expected counts. We have several categories, and I'm being generic and talking about the ith category. Let's let K represent the number of categories, and let N represent the number of independent trials. Okay, so going back to our household incomes, N would be the number of households. Okay, we talked about that already. That's going to be 1,500. That's the number of trials. Each selection of a household is like a trial in which you find out which category the households fit into. And then the number of categories is what we're going to call K. So in this example, K would be 7. Okay, and we're going to come back to this example, so you'll have a chance to write this stuff down again for that example. I just wanted to explain it while we were being introduced to this notation. Okay, anyway, with all that in mind, the test statistic, it's a chi-squared. It's the sum over all the categories. So you do this once for this computation once for each category and then add up everything you get. Observed count minus expected count, square the difference and divide by the expected count. And with chi-squared, you also need to know how many degrees of freedom. It's K minus 1 degrees of freedom. In other words, the degrees of freedom are number of categories minus 1 degrees of freedom. Now we may need to know when we can use this test. So this method with the chi-squared, with this test statistic, when can we use that? And yeah, now we can go on to this. Okay, the expected count has to be greater than or equal to 1 for all the categories. Okay, you can't expect 0 or negative counts. Negative counts wouldn't even make sense. And then, but they can't be less than 1. So you can't like have an expected count of 1/2 or something. And then no more than 5% of the categories can have expected count less than 5. Okay, that was a lot of information, so I think we're going to stop there and we'll come back and return to our example of the household incomes and actually perform the hypothesis test for goodness of fit. And I'll see you in the next video for that.